events that are open to the public. We call them talks on tap. They're kind of like democratic discussions. Every month, we do it once a month. Every month's a different topic. So we've talked about everything from mental health to clean vehicle emission standards to social entrepreneurship, like you name it. It's what the audience wants to talk about. And we bring the experts and we have a talk at someone's house and have Costco pizza, the American favorite, for dinner. So I'm going to pass this around if you're interested in it. The QR code is on the back. It is a public event, but the only way you know about it is to be on the invite list. So I hope you enjoy the event tonight, and I look forward to your questions.
Okay, thank you everyone for coming this evening. If you just wait momentarily, we'll be starting at 5:30. So get comfortable, we're still letting some people come through, and yeah, get excited.
Not hello. Oh, so this is not mute. Sorry, I'm bad with technology, so you have to put up with me for the night.
I just want to check with people online. Can you see us through the camera? If you could, please feel free to type in the chat. Yep, awesome. Thanks. Oh, hi, Matt.
Hello, hello. Okay, glad to see the microphone's working. We got some very dramatic and cinematic blinds going on here. Yeah, we need the Star Wars entrance right now. Okay. Well, welcome everyone to the ANU Astronomy Society Rocketry Society Symposium combined with the US Embassy, which has brought representatives from all the way across the world from NASA, JPL. And tonight is going to be a very interesting series of talks that we're excited to present to you. So I want to say a big hello to all of the other states that are joining in with the Zoom. Give a little hurrah in the chat if you can hear us. If you can't, that is quite concerning and we will fix that. But for now, I will introduce Alan, the chair of this event, and he will be giving a proper introduction as to what tonight is. Thank you all for coming.
What is it working? Hello? 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 Ah, it's kind of working. That's fine. Yeah, you do. So welcome to country. Oh, hi everyone. How's it going? Yay, come on. Oh, all right, here we go. Thank you. Thank you, Jess, for the amazing intro. I would like to welcome you all to this year's Space and Astronomy Symposium. Some of you might know, Astronomy Society always run a symposium at least once a year. I think this time we're doing twice a year. Maybe? No? Maybe? Maybe not. Maybe not. We're a bit tired. Thanks for traveling through around Canberra to be here. Some of you traveled through Pacific, and it's quite amazing. Before we begin, I would like to acknowledge the traditional custodian of the land on which we gather today, the Ngunnawal and Ngambri people. We pay our respect to their elder, past, present, and emerging. And Indigenous Australia and we acknowledge Indigenous Australians were among the first astronomers on Earth, using stars for navigation, storytelling, and understanding the cycle of nature. Their knowledge of the skies continue to inspire us today. We also extend our respect to the indigenous people across the world whose deep connection to the cosmos might have shaped cultural tradition, scientific understanding, and way of knowing. We're continuing as our global appreciation space. Yeah, cool. Yeah. So this event would not be possible without amazing help from NASA, JPL, the US Embassy at Canberra, ANU Rocketry, and the ANU Research School of Astronomy and ANU Research School of Physics. Their invaluable contribution to planning and organizing this symposium is greatly appreciated. We also thank the ARC Center of Excellence for Gravitational Wave Discovery for funding this event. And I would like to express my gratitude to amazing speakers for tonight, Kevin, Susan, and Carmen. Sorry, Elisa. Sorry, my bad. This event is being, as Jess mentioned before, this event is being broadcast on Zoom. We have University Hub across the country watching us. So that is University of Sydney. Hi, USyd. Perth Observatory, Gingin Gravity Discovery Centre, UNSW, University of Western Australia, University of Adelaide, University of Queensland, Macquarie University, University of Melbourne, Monash University, and University of Tasmania. So huge thank you for everyone online as well. So astronomy is one of the oldest science, yet it remains one of the most exciting, well, to me at least, frontier to human exploration. Every day we uncover new mysteries about our universe, from the smallest exoplanet to supermassive black hole. And while the universe is expanding, so is our knowledge and our curiosity. And if you have anything like me, my collection of space socks. Anyone collect space socks here? No? I thought that was a thing. It was a thing, maybe. So each talk will be about 10 to 15 minutes long, followed by a Q&A session. For the live audience, we would have a couple of runners around here with a mic. So feel free, if you have a question at the end of the talk, put your hands up and we would give you the mic. And so let's embark on this intellectual odyssey together. Let's challenge ideas, spark new discovery. Above all, remember to look up both figurative and literary speaking, because whether you're astrophysicist, amateur stargazer, or just here for the vibes, ChatGPT is not doing a good job here. We're all connected to the same sky. So welcome to the Space and Astronomy Symposium. Thanks. What? Oh, no, that's not for me. No one should ask me a question. Here we go. Have fun. If anyone online want to scan that code, we'll keep it up for a moment.
Okay, so take a moment to recognize this QR code. So if you have any questions throughout tonight, please put them up on here for our question session at the end. But at the end of each talk, we will be opening up to the crowd, to those on Zoom, and we will be asking the audience. Okey-dokey. Perfect. So I'd like to introduce our first speaker, Kevin from NASA. So it is a very big name to announce, and I'm honored to have you representing NASA tonight at the Physics Auditorium. So put your hands together for Kevin.
Thank you. Look, I'm just Kevin. I like that. No, I love it. Hi, I'm Kevin Coggins. I'm the Deputy Associate Administrator for Space Communications and Navigation at NASA. It's a long title, but I like the title, this other title better. I'm the Head of Extraterrestrial Communications for NASA. See, that's better, right? So I'm in charge of all of our infrastructure around the world that we use to talk to near space and deep space. Near space being, the surface of the Earth to the moon, deep space being around the moon to everywhere out, all the way into interstellar space where the two Voyager probes are. And joining me tonight is Susie Dodd, right here, who is both the lead for our deep space network, but also the project manager for Voyager. So she's been working Voyager for a long time, and I'm excited to hear what she has to say too. So let's just talk about deep space real quick. Did I do it? There we go. So, we've worked with Australia for a long time to do amazing things in space. And it all started back, in the days of going to the moon and even before. Anybody heard of Auroral Creek or Honeysuckle Creek or Auroral Valley, right? Any trackers here? Any trackers? The trackers are the people that worked the Deep Space Network in the early days of space exploration. We just celebrated 60 years of the Deep Space Network relationship with Australia in Canberra just yesterday. We had about 300 people, a lot of retired trackers, some of the people who were responsible for building the biggest dishes the world has ever seen, the 70-meter dishes. And there's a long history of Australia and NASA and space. I'm not going to read the charts. I may not even flip them if I can't figure this out. So it's the Canberra Deep Space Communications Complex. It is one of the most beautiful space sites in the world. Any of you guys ever been up there to see it? Good. Were any of you up there yesterday for the celebration? Some? Good. Outstanding. Oh yeah, of course, you guys were with us. So we had about 300 people there, right at the foot of the 70-meter antenna. It was amazing. We had some of the people that helped build the site, that operated the site, that made the voices of the astronauts who landed on the moon come to the Earth, right? Receive that, one small step for man phrase. That's incredible. But that's just the beginning. Every day, 24 hours a day, 365 days a year, there's some space mission talking to the antennas in the Deep Space Network. When the sun is on this side of the world, the trackers at the station in Canberra control all of the network around the world. The dishes in Madrid, the dishes in California, and the dishes here. When the sun goes down, the next station, when it's got the sun up, is controlling the antennas. We call it the follow the sun model. Data from space missions all over the solar system and beyond come into this network. showing us things that you're probably studying in your classrooms, amazing things. But it's not easy. Some of these dishes are, 60 years old, and we have to maintain them. Some of them are brand new. So one of the things we did while we were here is we went to Western Australia to look to where we're going to put a lunar antenna, right? Yeah, we call it our LEGS antennas, our lunar exploration ground sites. Their antennas we're putting here in South Africa and in New Mexico, so that we can kind of focus on the moon with these antennas and not make the deep space network focus so close on the moon and keep it focused on the missions that are orbiting, the sun or Europa Clipper, right, heading to Europa. When I go into the control room for the deep space network, I always like to talk to the operators. They get to sit at the console and watch the data come in. They get so excited. One of them, he posts on Twitter all the time. Yeah, you guys know, the real-time things happening, whether it's a lander on the moon or something cool that Voyager's doing. And Susie, I hope you're going to talk about the peril Voyager was just in, right? I would love for you to. It's just exciting that the work that these engineers do to keep some of these space missions alive. And if it wasn't for our ability to do deep space communications, we wouldn't be able to get this data for decades. All of the network, most of what the network's done to date is radio frequency communications, right? In microwave frequencies and other frequencies. But now we're starting to introduce optical as well. And I'm just going to skip around. Well, I'm going to say Voyager for you, Susie. And I'm going to skip to the optical work we do. How many of you guys have ever worked optical or lasers here in college in your physics department, right? Okay, what's the hardest thing about optical? Weather. That's the atmosphere, right? And so these antennas are on the ground of the Earth. And so we're subject to whatever's happening with precipitation or cloud cover that can mess with, this optical beam. But what's the big advantage of optical? Somebody said it. The bandwidth, right? Bandwidth is how much information I can squeeze in there, right? And you can get a ton in optical. So when I aim the 70-meter dish at one spacecraft that's got a certain data rate, maybe I'm locked onto it for a couple of hours to get all that data down. Whereas optical, maybe that takes me 5 minutes, right? That means I can do a lot more things with optical than I can with some of these older RF technologies. But the RF technologies can punch through the clouds. So it's trade-offs, right? So the future is going to involve both. We've done some amazing things with optical, with Psyche, right? Talking to it from long distance away, to we had a SpaceX satellite that had this laser called plug-in placer talk to the Polaris Dawn spacecraft while it was moving through flight. So the first optical link to a powered spacecraft from a satellite, and that was amazing. So space-to-space optical is a big thing we're looking at, but we're also looking at deep space optical as well when we can use it. All right, I hit you guys with a lot. I'm trying not to take up more than my 10 minutes, but what I really want to talk to you about are your questions. So open for questions. Yes. Good question. So when I talk radio frequency communications, I'm talking about the traditional frequencies like X-band or S-band, or things that we measure in megahertz, right, or gigahertz. Things that we use antennas to radiate and receive. When I'm talking about optical, I'm talking about laser diodes, right, shooting things in the optical frequencies. Specifically, 1550 nanometers is what we've kind of tried to normalize everyone to, which is the same technology we use in fiber optic data links here. And so we get to reuse commercial technology and things we've already learned in the space layer. Does that help? Thank you. Yes, sir.
That can't be punched through clouds. Is there any, or has there been any work on doing like an aircraft to space transmission? Because surely that would be able to get you above the weather in a cheaper way than a spacecraft.
Yeah, absolutely. So we had this payload on the ISS called LCRD, right? There's a laser communication demo. And we have a spacecraft at an aircraft at Glenn Research Center that had an optical terminal on it. And so one of the things we tested was the ability for this aircraft to fly and connect to the ISS through that optical link. So yeah, great question. And you guys can Google that and look that up. It's a really neat project. Yes, sir.
Yeah, so my question was just going to be, in the time that you've been doing this job, what's been the, say, single biggest innovation that's changed the way you do your job? Or maybe another way of thinking about that is, how much has it changed since when you started compared to now?
So I've been doing this job for 13 months, right?
Fair enough.
Right? And so if I really squeeze in that window and look at the single biggest innovation, I'd say it's the single biggest innovation I've learned about at NASA, and I'd call that delay tolerant networking. I think that is a huge change for how we do space communication. So on the Earth, you guys are used to internet packets moving around, right? And if you drop a packet, you reach back and have them resend it, right? Space is a little different. These distances are vast. Voyager, it takes what, 23 and a half hours for the trons to get there and to get back at the speed of light. So imagine if the Earth wasn't in view at a given time, but there was a satellite on the other side of the moon, right? And delay tolerant networking means we're designing the network where we can deal with these delays and interruptions and blockages that can occur in space when you can't see something, can't radiate to it. And these packets will get stored in a special way, and when it does make contact, it can come through. It's a networking protocol that makes a lot of sense for things that are going to suffer disruption. And so for me, that's a big deal because this is a massive amount of data. And the one thing in science that I learned at NASA in my 13 months is they don't like to lose any data, because in that little bit of data might have been the discovery. So they want all the data they can get whenever they can get it. That's why we have so many space missions that they were planned to operate for this long, but the satellites survived. Do you think they turn them off? No, they want all that data until that satellite can't provide it anymore. So great question. All right. Yes, sir.
If you wanted to say talk to a craft the same distance toward a laser-based communications, wouldn't you be limited by material science, like how good you compare optics with the laser? Or would you be limited by how well you point the laser at the spacecraft?
Well, so that's a great question. I don't think pointing would limit us because we've come up with techniques to kind of kind of accurately dither a laser. But the best technology that I know of and the best people at pointing things are the Deep Space Network in pointing these antennas and pointing at Voyager at all. So I think with the techniques we have for moving lasers around and to get on targets and find them, and the expertise at pointing these dishes while the Earth is rotating, by the way, at things also moving, would help us. I think the issue you're going to hit is the distance, things that are going to happen with diffraction of the laser, the amount of power you're going to have to use. I think those are going to become the issues. We've done really distant laser links into space, but nothing on the order of how far Voyager is. That's incredibly far. I'll let Susie talk about how far it is. I mean, it's incredibly far. And plus, it's in interstellar space where there's a lot of stuff going on that could probably interfere even more with the optics. So great question. Yes, sir.
You mentioned the new packet information that was being stored in other spacecraft, etc., and also about the extended service life of certain missions. Are you guys continuously giving software updates to old spacecraft like Voyager? Are they receiving new technology and new updates, or are they just running old the stuff that they launched with, and you're dealing with that?
So I was at the. I'm going to tell you a story to answer that question because I love this story. You know the story I'm going to tell. So I just started with NASA. I'm out at JPL. We're having meetings on the DSN. Susie comes in and says, "Kevin, at this time, Voyager 1 was having issues, right? We couldn't communicate with it. Things were messed up." And Susie said, "Kevin, the Voyager 1 anomaly resolution Tiger team is meeting, and I think they've discovered some things. Do you want to go to the meeting?" So I sprinted out the door, and she said, "No, Kevin, this way," right? Because I was running past her. I wanted to be in there so bad. So I go in this room, and Susie's like, "All right, let's just sit back here." So we sit back here. There's there's 5 or 6 or people on VTC. There's people in the room. There's a couple of retirees on there who came back for free just to work this. They had just gotten some data back. By the way, when they send data, it takes 23 and a half hours to get there, 23 and a half to get back. If it's coming back on a Sunday, they come in the office. They want the data as soon as it comes in. So they're talking about the problem. Well, I guess there's one guy who talked in hex code. And if you told him some hex code, because it's all in hex code, he'd tell you exactly what that meant, what subroutine that was, why it was written that way, right? You had a young engineer who knew Python, right, who wrote some algorithms to actually find the signal in the garbled mess that was coming. You had like somebody you called the keeper of knowledge. I can't remember her name. Yeah, but she knew where everything was. I mean, they had reams of yellowed schematics, TTL circuits, memos everywhere. She'd be like, oh, that's over here. They had a memo that had a bootloader program that they pulled out, and they copied the hex out of it to use it. But they figured out it was bad memory bits. They rewrote the code, new code, software update, pushed it through space, flashed the spacecraft, and fixed it. That's incredible. At distance, without ever touching it physically. Nobody's hitting the reset button, right? They're doing it through these big dishes, the biggest dishes. In fact, there's a picture that I wish we had in the presentation where they arrayed 6 antennas in the Deep Space Network to use the array to receive and maybe send some of that signal. But so the short answer is, yeah. And when it's an old spacecraft, it's amazing to watch. And it took them a long time to do it. Was that accurate? Okay. It's pretty exciting stuff. Yes, ma'am.
Like the rise of Starlinks and getting more satellites out into space, whether they interfere at all with your non-optics?
So great question. So my other job at NASA is I'm in charge of all the spectrum, right? From a perspective of adjudicating to make sure there's no interference when people file for licenses that might use the same frequencies as us, including SpaceX, because we use some of the frequencies that are near each other or some of the same frequencies. And the answer is no, because we work, SpaceX and others are very good stewards of spectrum, and they work very closely with us to make sure that they say, this is what we need to do, here's how we want to do it. If there's an adjustment, we have a process where we say, okay, you can do that, but maybe adjust your power here or your frequency there. And so it works out pretty well, and we do it on an international scale, not just with SpaceX. We do it with other countries and their space missions, because we're all moving up there in this physical space, but we're all in the exact same spectral space in some cases. And so it's just a process we have to follow to make sure that there isn't interference. And when you get to higher frequencies, you're not like broadcasting in every direction. You're broadcasting very specifically at that direction. There's a little energy that comes out the side, but you try to reduce that so that I'm really focused here. That means if I'm over there, I can use the same frequency to talk to Susie as I can talk to Caitlin from a different place and not interfere. And so it gets complicated, but we have to coordinate a lot to keep from having that interference. So far it's working great. Thank you. Any other questions? Yes, sir. One more and then I'll stop.
Hi. So obviously, like SpaceX, other private companies are becoming bigger in the space industry.
Yep.
But NASA is still doing a lot of the space communications. And I'm just wondering, what is it that NASA as an organization can do that perhaps a private company like SpaceX might not be able to with regards communication?
Well, congratulations on having the first question that they can hear on Zoom tonight. And yes, very good question. So, when back when we were doing Landsat, we needed more antennas around the world. So we built some in Norway on an island called Svalbard, right? Svalbard, up in the Arctic Circle, 76 degrees. And after the mission, we were like, what are we going to do with this antenna? And there was a company You know, the Norwegian government wanted to form a company, and they had, they had KSAT and some things. And they're like, well, what if we take it off your hands and we'll start a commercial business around these ground antennas? And so KSAT started. Right now, they're one of the largest ground, system providers in the world. We use commercial companies all the time. Swedish Space Corporation is another one that has these ground antennas all over the world. We have a very old satellite called TDRS, right, which is what we call a space relay. We have a rocket that's going to launch. It makes some links to TDRS so we can get all the data off of it. It launches. We track it through the atmosphere. It gets in low Earth orbit, does something, talking to us the entire time, and just sending a signal that bounces, that we bring it back down to the Earth so people get the data off of it. Space missions around the Earth use it. The ISS uses it. That's how the astronauts get video and voice. Anytime you see anything come from the ISS that you see on YouTube, it came through the TDRS system. TDRS is old. We built all these things before there were commercial markets. There was nobody else to do these things. The only reason you need to do them is because of what NASA was doing. And so, but now you have telecom providers like Iridium, Viasat, right? SpaceX, Kuiper, that now have businesses of putting satellites up to do communications to the Earth. They put them in LEO, MEO, and GEO. And so we have this program at NASA called CSP, the Commercial Services Project, where we're paying them to demonstrate their capability to us so that we can buy it from them instead of use our system, which we're going to retire. And so we did it this way because we wanted their investors to see that we were interested in paying them so that the investors would invest in helping them build out their constellations. So we're helping build a commercial space economy, right? And so because where there's a market for commercial, NASA, we should encourage a commercial economy to grow so we can buy services. And we step into the next thing where there is no commercial basis, right, for business. So you look at the moon. Well, we want to go to the moon with Artemis, right? And we have all these landers that just went up, but we want them to be able to talk back to the Earth easily. So we awarded a contract to a company in Texas called Intuitive Machines to put lunar relay and GPS around the moon, but as a commercial service, so that anyone who goes to the moon can just buy it from them. So the contract we gave them was just to validate what you build, that it, show us that it meets our requirements. And so again, we're standing up a commercial company, but no one's going to stand up a commercial company to talk to Voyager or Europa Clipper because NASA's the only one there. There's no commercial basis for business. But with all these things going to the moon, there sure is. With all of us on the Earth, there sure is. I mean, some of our phones talk to satellites, right? And so when you ask the question, what can NASA do that industry can't? I would say, where should NASA spend their money, right? And our partners spend their money to do what industry can't, right? Or won't, because it doesn't make sense for them. NASA has the experience today in deep space, but when deep space becomes something where we're mining asteroids and, we have a lot more business case with Mars or wherever else, those are going to become commercial businesses, and NASA will step into the next thing that needs to be done, right? Whatever that is. So I hope that answers your question. Thanks. Can I do one more? Oh, one more, then I'll stop. Okay, oops. All right.
Cheers, thanks, Seth. Yeah, so on the topic of commercial companies, and you've spoken about Intuitive Machines, about, I think 2 weeks ago, they had that recent landing, and unfortunately, I guess some said it was a bit of a failure. But since they've had a contract with NASA, and I think they have another 2 coming up, what's NASA's take on, something like this? So there was another lander, I think, Firefly, that did successfully land on the moon. Now, would NASA kind of shift towards the successful companies and take, what's the best available? Or would they be more supportive, do you reckon, towards these companies that do want to start up and want to expand and, potentially go for deeper and longer partnerships?
So this is a very good question. Many of us weren't alive in the early days of NASA. Some were, but NASA blew up a lot of rockets, right? And we crashed a lot of things, and that's how you learn. And the value is not necessarily in the one piece that makes the news. It's in all the things they achieved on that flight. And Intuitive achieved a lot of firsts on that flight, and so did Firefly. In fact, on Firefly, we had a a GNSS receiver that received Galileo and GPS and showed that we can receive those signals on the moon. They won't give us the precision here on Earth, right? But it's a signal and it's time, right? It's time transfer over that'll help us with a lunar coordinated time when we set that up. So each of these landers, even if they have some anomaly in how they land, they're achieving so much, but they're also exercising a commercial business to learn, right? To learn how to manage that risk, the risk inherent in trying to land on the moon, or operate electronics on the moon from a battery, and when you got to keep it cool, when it's not a good environment to cool things down. You can't like blow a fan. And so all of them, every single one of these landers had things that didn't go perfect and a lot of things they learned. And so in NASA, we're in the business of science and discovery, right? And exploration. And so we look at every detail of what we're able to discover and build upon. And then we correct the things we need to correct and we just keep going. But great question. Okay.
Okay, we've had some really good questions from the audience. And now we'd like to ask one that was given to us from Perth in Western Australia. What was it that got you into this job and/or this line of work in particular?
Oh, thank you. I was just in Perth and Geraldton. It's beautiful out there. When I was a little boy, I lived in the state in the United States called Florida. And one of the things I like to do is, I'm a dreamer, I'm an optimist, but look at the stars, right? On a night where you can see the Milky Way. And I've always been fascinated with physics and engineering, black holes, gravity waves, all these things. Then I went to college, got my electrical engineering degree. I worked for a long time, did a lot of cool things. And then I had this opportunity to take a job at NASA, bringing it all together. And so I felt like that little 7-year-old kid again, like I had that opportunity to go live a dream and work with people like Susie Dodd that, have helped us discover things about our universe that no human's ever known before. It's amazing. So I'd say it's a boyhood dream come true from a lot of hard work. So thank you for that.
Testing. Okay, thank you very much. So I'd like everyone to give a very big round of applause for Kevin here. Thank you. And now we will introduce Susie Dodd up into the stage. We'll get you mic'd up. Oh, lovely. You're a step ahead. Perfect.
I have the mic, and I think you can hear me, right? Everybody can hear me? Thank you for the thumbs up.
Okay.
All right. I actually think, Kevin, I have a pretty cool title. Okay. I'm the director for the Interplanetary Network Directorate. So this is what we do at NASA. We challenge each other to come up with cool titles. As Kevin mentioned, and I appreciate him saying this, I'm also the Voyager project manager. This talk in particular, at least the slides I have, is more about the Deep Space Network, because our directorate at JPL is responsible for operating the Deep Space Network. But I'd be happy to take any questions that you might have about Voyager too, and I'll sprinkle in a few Voyager facts as we go. Not that direction.
Sorry about that.
Okay, can you keep going? Love the t-shirt. Okay, if you're not familiar with the Deep Space Network, it's a set of antennas and it's located equidistant around the Earth, so that as the Earth turns and your spacecraft is at Mars or further, one of these antenna sets can point to your spacecraft. So your spacecraft could actually have 24-hour coverage as the Earth rotates around. The countries involved, if you're, oops, you got ahead of me. Did I do that? I'm on the way. There we go. Okay, got it.
I'll flip it for you.
Okay, sure. Thank you, Kevin. So the countries involved, if you recognize the flags, you have the United States. Our tracking station is in Goldstone, California. It's halfway between LA and Vegas, okay? In the middle of the desert on an Army base. So it's kind of unique in that aspect. You've got the Kingdom of Spain in the middle. So outside of Madrid, there's a set of antennas. And then right in your back door here out in the woods is out in Tittenvilla is the Australian complex. And that is an image of a 70-meter antenna. The dish is 70 meters. And each of the complexes has basically the same number of antennas. We're in the process of building out some antennas, and I'll talk about that. But it's basically 4 34-meter dishes and 1 70-meter dish at each complex. That's where we will be by 2030. And the reason for that is that if you array 4 34-meter antennas, you have the equivalent of 1 70-meter antenna as far as aperture gathering size. And so you have redundancy, right? You want to have redundancy. And then if you take antennas that are smaller, you can also break them apart. A mission like Voyager, or Kevin mentioned Europa Clipper, those missions need the big 70-meter antennas. But if you're at Mars, you only need like a 34-meter antenna. So you can group them all together 4, or you can just do them individually, or you can do 2, or you can do 3. So there's a lot of flexibility by having array capabilities of antennas. Now, it's slow. Okay, I mentioned where we're at. Also at the Jet Propulsion Laboratory, JPL for short, in Pasadena is our control center. So all of the data from these sites flows into JPL, and then it goes out to the different missions, and wherever around the world their mission operations centers are, that's where that data flows. And you can think about it in the sense that what's important here is we're all on the same standards. We're all using the same interfaces, and that's key for us to get data between all these antennas, and then also out to the mission operations sites. Involves a lot of software, it involves a lot of testing, but the key is we're all on the same standards. And then as far as geometry goes, the view period, you can see, I mentioned that as the Earth rotates around, there's a site that sees a spacecraft way out at Mars. But basically the Deep Space Network is able to go from slightly before the moon, but about moon range out to interstellar space. Now Voyager is the furthest spacecraft. Voyager 1, it's, if I get it in kilometers, it's like 22.5 billion with a B kilometers from us. Kevin already mentioned the one-way light time is 23.5 hours. If I'm sitting at a console Monday morning and I'm sending a command to a Voyager, how are you doing today, Voyager? Voyager gets it Tuesday morning. I get its response back Wednesday morning. So it's almost 2 days. We're going to reach a light day in early 2026, which will be a big milestone. But it's furthest out there. Voyager also launched in 1977. It's the same time the Apple II, big Apple II computer came out. Also, if you're a Bee Gees fan, they had some hit songs right there in 1977. They were like the #1 group in 1977. But in 2.5 years, August of 2027 will be a 50th anniversary. And we're very hopeful that we can make it there with at least one spacecraft. There's actually 2 Voyager spacecraft, and we're hopeful at least one can make it there. And that's going to be a big party, and we'll invite Kevin and all the DSN folks, and maybe we'll do a party tour at each DSN site, something like that. Next. And this is what the DSN does. We make these missions possible. And I'll start in the lower, you're looking at it, sorry, lower right, which was Artemis, right? We track the Artemis mission, and we will track future, at least Artemis 2 and 3 with astronauts in the future until the legs antennas are up and running. In the middle is James Webb, Starfield. The far left is Hayabusa, which I think landed in the desert here in Australia, Japanese mission that we tracked. DART was the asteroid redirect mission. We sent an imploder to an asteroid and then detected how much we could move it away from the Earth, essentially. The planet, think of it as planetary defense. Bruce Willis was not involved with that mission, but it's kind of like that. Juno at Jupiter, fabulous images. And then the Mars rovers, of course. And I left off the helicopter, but I think the helicopter is super cool technology. A helicopter on another planet. Can't imagine doing that. Next. Okay, so here's the first antenna right here out in Tittenbilla was DSS 42. And it started operations in 1964. And it lasted a long time, 36 years we got out of that. It was retired in 2000 when we started building the beam waveguides and retiring out the old antennas. So if we go to the next one, this is what a newer antenna looks like. This is 35, which was built in 2014. There's a duplicate of this that was built, DSS 36, that was built in 2016. So we really had two new beam waveguide antennas come here in Australia in the last decade. And the trick with the beam waveguide is you basically you might be able to see in this design, but there's optics and mirrors that are taking the signal down to an underground set of electronics. And by doing that, you don't have all this cable wrap that you have to worry about going this way if you're turning this way and then having to go back the other way to unwrap the cable. Because all your electronics is in the basement. It's actually much easier to fix and update. You're not climbing up to the top of the structure to update things. So that's why the beam waveguide design, which came on board in the 20-teens, is really important to modernizing these deep space antennas. Okay. And this is one we're building at Goldstone. This is the antenna lift. It happened in December. So we put the structure together and then the antenna together, and we set it on top of there. So that's DSS 23. And we just broke ground here in Canberra on DSS 33. DSS 33 represents the last of these beam waveguide antennas. It will build out these new sets of antennas, and we'll be done with that. It was a beautiful morning in the desert, a little cold, but you know, that's what it looks like. And that diameter there is 34 meters. So it's big. It was a big crane and a big day. Okay. This is my last slide. I have a board next to my office, and when I come in every day, I can see exactly what spacecraft is tracking on which antenna. This is publicly available, so I put the website up there. The Canberra antennas are on the bottom, Goldstone in the middle, Madrid on the top. But you can see where Canberra in particular is usually always tracking a Voyager spacecraft, whether it's Voyager 1 or Voyager 2. And what really makes me happy is I got both my spacecraft on here tracking at the same time, because Voyager 1's tracking up there on the 70-meter in Madrid. And it's a bit of a decoder ring to get the numbers and the sizes and the frequencies, because they're not all identical on the antennas. And one other thing I should point out, which is really cool, if you look at Goldstone, look at 26, you'll see 1, 2, 3, 4 missions. Those are Mars missions. And what's happening there is Mars fits into about the size of the beam of the spacecraft. So we can download data from 4 different missions at the same time because they're slightly different frequencies. So that's called multiple spacecraft per aperture. And that's another technology developed to make these antennas more efficient. So anytime there's a bunch of spacecrafts that are close together, we can, if they're not on the exact same frequency, we can track them at the same time. And we have technology to do that on the uplink side as well that we're still kind of working out, but it's there. The technology is there. So it's helpful for things like CubeSats around the moon or things like that, where you can track multiple spacecrafts at the same time. And I think that is actually my last slide. So happy to take questions. Yes, sir. I'll also try to repeat your question so that.
Thank you. I think Kevin mentioned earlier there was some mishap with the Voyager 1. I was wondering if you could share a bit more about that and your experience with it.
Okay, well, it was pretty stressful. Every day that Voyager doesn't have an anomaly is a good for me. It happened in November a year and a half ago. And we just stopped getting data from the spacecraft, essentially. And remember, these spacecraft are built in 1977. They are very old. And Kevin described the fact that we have paper documents that are yellowed and circuit diagrams that are yellowed that he got to see firsthand, people going through that stuff. But what happened is our flight data, well, we didn't get any data back, so we didn't know what was going on. So the Deep Space Network tracked Voyager and determined that it was getting a carrier signal, right? It wasn't getting telemetry, but it knew it was sending us a carrier signal. So they went in and looked at that. And after a lot of different kind of diagnostic things. They figured out that it was in our flight data computer. We have 3 computers. The CCS, which does the command and control, the attitude and control system, and the flight data system, which is the one that packages the data back to the Earth. So the one that was found in air was the one that was packaging the data. And we figured there was an error in the flight software. And after we brought in all the retired gurus who knew about assembly language flight software and had done some of the design on it, worked through it, they figured out that we had lost a piece of memory. And they could pinpoint where that piece of memory was. And they essentially wrote around that. They rewrote the flight software. We've never done a flight software upload to a spacecraft in interstellar space. And again, we're talking 23 hours one way. Nothing happens fast on Voyager just because of the round trip flight time too. I mean, it's 3 seconds to the moon, 20 minutes to Mars. It's 23.5 hours to Voyager. So you get a little dribble of data and you look at it. Then you got to go send another command and see what that comes down there. We got on from a operations standpoint, we got on a pretty nice cadence of sending a set of commands every week, typically on a Friday, getting the data on Sunday, spending in the beginning of the week looking at that and deciding what the next set of commands we wanted to do next Friday was. But that whole process was a 5-month process. Yeah. Right behind you is a young lady there.
Sorry. You mentioned before that you can do multiple tracking of through your networks if they're on different frequencies or different networks. I was just wondering, is it possible to change the networks or the frequencies once they are out in space, or is that a limitation that exists?
Actually, that's determined, I believe, by the spectrum at first, right? So you're assigned a frequency, and you're approved by the world governing radio body for that frequency. So I don't believe that you can change it. Kevin might know a little bit more.
You just have to go.
Yeah.
But typically we use transceivers that are programmable. And so I mean, you could.
That doesn't come up very frequently. Yeah. Anywhere, choose one.
Hi. So from what I understand, we're communicating with Voyager every day. It's sending data to us. We're sending data to it. What kind of value can data from Voyager 1 provide for us nowadays?
That's a great question.
Traveling, through the void for the most part.
So Voyager 1 crossed into interstellar space. Interstellar space is defined by where the edge of the sun's influence stops and where we're traveling through interstellar space. In other words, we're not sensing any charged particles from the sun anymore. So Voyager 1 crossed in 2012. Voyager 2 crossed in 2018. Both about the same distance, 121 astronomical units from Earth, which is interesting because they're going in different directions. Voyager 1 is up and out of the plane of the planets, and Voyager 2 is down and out of the plane of the planets. Still toward the nose of the heliosphere, but different directions. So that was the first interesting feature. But what's most important about Voyager is the duration that we travel away from the sun, and how what Voyager is traveling through changes, how interstellar space changes the further we get away from the sun. Because at first the plasma density grew and then it flattened off, and you say, okay, when it flattens off, we're in the true pristine interstellar space. And then 4 years ago, it jumped up again, what we're calling pressure front 2, a pressure wave. It jumped up again, the plasma, and it stayed flat. What's that all about? We don't know. Scientists don't know. But really what's the most important is just the longevity of this data that we can get as far away from us as possible. And the spacecraft is sensing fields and particles, magnetic field from the sun or interstellar space, but mostly the sun's magnetic field and how that's entangled with the sun's magnetic field. And then the density of the plasma. No cameras, those are long gone. And because of our power limitations, it's a nuclear power, radioisotope thermoelectric generator, loses 4 watts a year. We are now turning off instruments because we don't have anything else we can turn off. So, and you can hand the mic to the woman next door to you. Oh, she's already got it.
Hi,
Great,
Susie.
sorry.
Thank you. I'm a master's student in the Applied Cybernetics program here at ANU, and I'm wondering what the impact is and use of neutrino science on the DSN and communications.
I don't know the answer to that. I don't know if there's any neutrino science impacts on the deep space network, so I can't. Kevin's shaking his head too. I don't think there is any. I mean, it's radio frequencies primarily and optical that we're working with. We got one behind you. We'll make our way down here.
Hi. So it's clear that there are very complicated mechanical and algorithms in tracking and talking.
Oh, charge, eh?
Just shout really loud and I'll repeat the question so that people online can hear it. The biggest obstacle when talking to Voyager is just really the distance. And because of the distance, you can't do very high transmit bands. I mean, not transmit band, the data volume, right? Very low. Our regular data rate of Voyager is 160 bits per second. Everybody in this crowd probably doesn't even remember what a modem is like, but that's kind of the speed of a modem. So it's really all about data and how much data you can get back and how fast you can get it back. And that's why, you know, if the astronauts on the moon or when they get to Mars, if they want to see their football games in high definition, their cricket matches, you know, that's optical. That's high data bandwidth. So and that's what we're working toward is really the higher frequency, higher bandwidth data. Okay, you have a mic. Let me know when you want to cut this off.
Wait, Max, then Max, then we will go for 2 online questions.
It's great. I mean, I love having all the questions, right? It's great, yeah.
I had a question. In terms of, we're dealing with a very wide range of how old our different probes and instruments are. In the next 1, 3, and 5 years, what are you most excited for? If that's technology or projects coming to maturity, what are you most excited for?
Well, I can name a few things. I'm very excited about Voyager making it to 50. That's a personal goal, and it's a goal that NASA has when I talk to the NASA people. So that's August of 2027. I'm looking forward to DSS 33 completing right around 2029. That will complete the DSN aperture enhancement project that we've been working on for 15 years now. And I would like to see a Mars sample return mission launched in the next 3 to 5 years. We have samples on Mars. We have rovers driving around on Mars, picking up test tube size drilling and taking a core sample, right? It's not a scoop, it's a core. So you can see the stratification in the core, putting that in a little test tube and dropping it on the surface. We need a mission to pick those up. And I'm hopeful, and I guess hopeful is a good word. I want to see that happen. It can happen. The technology is there to make it happen. We just have to have the willpower to do it, I think, and invest the money to do it. So, is that good? Oh, we got one more. Okay.
Yeah, one more from me. Kind of following on from that, but I guess if we think even deeper into the future, eventually we're going to have missions that are getting further and further away from the sun, potentially going to other stars as well. I suppose that the technology for that is probably also quite far away, but what might that look like? Is there the potential for networks on other worlds in the solar system, or how might we even go about that?
I mean, we're building out a network now around the moon as we start going from the program from humans to the moon to humans to Mars. There'll be a network of communication satellites there that can talk to, they can talk to astronaut landers, they can talk to rovers, they can talk to the astronaut when it walked off, you know, to when it went where it wasn't supposed to. No, just kidding. But it can talk to all the different assets on the Earth and transmit that data back to Earth through an orbiting spacecraft. So that's stuff that's all in design today. I can tell you that at JPL, we're talking about a potential network around Venus, because there's a potential to have three science missions at Venus at the same time. And how would you craft a network out of that around Venus? The same way right now we have a network around Mars, but that network at Mars is made up of orbiting science spacecraft. And we would like to have just dedicated communication satellites up there, as opposed to, well, because they're a lot cheaper and it can be dedicated to the astronauts when they're on the moon. So, okay.
Okay, lovely. So we have a question from online as well. Sorry, one last one.
I'll stand up so you can answer.
Yeah, from the University of Queensland in Brisbane, we have a question asking, how did you get involved in the Voyager program? What specific backgrounds in your education do you feel have had the greatest impact in your work?
Okay, again, an excellent question. I think everybody that comes up and stands up and is of a certain age loves to talk about how they got into the business. I went to a school called Caltech. Some of you may have heard that. A little school down the street from JPL. I have an engineering degree, a mechanical engineering degree, actually. I didn't do any mechanical engineering. So there you go. I got an opportunity to get onto Voyager for the Uranus encounter. So that dates me, but 84, I'll give you a date, 84. And I was doing sequencing. So I was in the operations side of the spacecraft, laying out what activities it was going to do and generating the commands to get there. And I had several job offers, but the one at JPL was probably by far the most unique. You know, Voyager was going to go to Uranus. When are we ever going to go to Uranus again? I'm still asking that question, you know. Nearly 40 years later, I'm still asking that question. But so I took the job that was kind of the one in a lifetime opportunity, and I just got hooked on space. And so I stayed at JPL and I worked at a lot of different missions, and I got into the DSN almost about 10 years ago. And it's sort of the other side of mission operations, but it's extremely valuable. You know, your Formula Ones in Melbourne, they don't run around unless the roads are very smooth and don't have any potholes and work with, you know, 24 hours a day. That's kind of the way the DSN is to these missions. It's the infrastructure that makes the missions happen. The data doesn't come back. The scientists don't make the discovery unless the Deep Space Network is there and operating 24/7. As far as the class that was probably most useful, you know, honestly, I think it's math in all its forms, but I think it's also a bit of history, knowing what's happened and knowing how to learn from mistakes and not repeat them, and communication skills. Because you don't work in a vacuum when you work in the space business. You have to work with teams of people. So you have to figure out, you know, how you get your points across, how you take the strength of each person in that group to build the solution. So communications is very important too.
Thank you very much, Susie. So that was incredible. It really showed how all across the world astronomy really connects everyone together. And so we're going to show a little bit of our connection here at ANU to astronomy. So I'd like to welcome Callum from CGA, the Centre of Gravitational Astrophysics. And he's a recent PhD graduate, and he's going to tell you all about his work.
Awesome. How about that? Is that better? Brilliant. Awesome. Thank you. Thank you all for coming out tonight. So yeah, I'm Callum Sandbridge. I'm a postdoctoral fellow. That's the first time I've actually said that out loud. I only graduated. Thank you. Yeah, whatever.
I only graduated back at the end of January, so all this stuff's very fresh. I have the pleasure today of being the sort of custodian and bringer of knowledge on this really exciting and young field, which is gravitational wave detection and astronomy. We'll be talking about that a little bit today, but also sort of the role of space-based science and in that field and kind of where that's going. So 1.4 billion years ago, two black holes collided in a merger that for about 200 milliseconds released 50 times as much energy as the rest of the observable universe combined. This energy wasn't released as electromagnetic radiation or a kind of slew of high-energy particles, though. It escaped this merger as ripples in space-time, gravitational waves. These were kind of predicted and formulated in 1916 by Einstein, whose theory of general relativity suggested that gravitational waves would manifest as ripples in space-time. Space tells matter how to move, and matter tells space-time how to curve. But if you have a dense enough pocket of matter and you move it violently enough, it can cause waves to propagate out through space itself. Einstein also said, though, that gravitational waves would be too small for us to actually observe. However, 100 years after this, and 1.4 billion years after that merger I discussed before, those gravitational waves made it to Earth, and we saw them. We saw them at the Laser Interferometer Gravitational Wave Observatories in Hanford, Washington, and Livingston, Louisiana. These observatories consist of a central building, which you can sort of see, and two perpendicular 4-kilometer arms. These 4-kilometer arms witnessed the space-time in that arm fluctuate on the order of about 1,000th the size of a proton. Do we have sound on this? Yes. All right, well, we'll see if we do. It sounded like, I'll let you plug it in. That's okay. Don't worry about it. Go back to the slides. I can do it with my voice. I've heard it a couple of times. Yeah, does anyone know what it sounded like? Yeah, I heard it. All right, we'll see if we can hear them. This is taking those gravitational waves and converting them into audio. Oh, maybe not. It was like it was a chirp. It went just this little 200 millisecond chirp. But oh, there we go. Inside that chirp was this rich, dense package of information about the two black holes that merged, their masses, their spins, and the observation of that chirp marked the dawn of gravitational wave astronomy, a totally new way of looking out into the universe. That was 10 years ago, and since then we've been busy. There's an international network of detectors now, and over the past 10 years, they've observed a cumulative 298 gravitational events. These mostly consist of mergers of binary black holes, but on the rare occasion, binary neutron stars, which are particularly exciting events because we can look for electromagnetic counterparts and follow up for them. These detectors kind of vary a little bit in design, but they largely all follow the same sort of basic functionality, which I'm going to very, very much simplify today. They measure this tiny fluctuation in space using lasers, an ultra-precise tool for measurement that I'm sure you're familiar with. In these detectors, a laser inside that kind of central housing unit produces light, which is split and shoots down those 4-kilometer arms where they hit these massive mirrors before the light is reflected back to that same beam splitter. Now, these mirrors are very carefully placed so that the light from both the arms coming out, the kind of measurement port of that beam splitter, deconstructively interferes, perfectly cancelling out, making it so that there's basically no light coming out. This deconstructive interference is completely dependent on where those mirrors are placed. So, as a gravitational wave propagates through the detector, and it kind of propagates like this, it's this sort of wobbling, space wriggling thing that comes through the perpendicular arms, it causes the position of those kind of back mirrors effectively to sort of wiggle in and out in kind of opposing motion. What this wiggling does is it causes that deconstructive interference of light to change, and we get these like little flashes at the output port of the detector. By measuring those flashes, we can reconstruct the gravitational wave and get all of that rich astronomical information out of the waveform. These detectors have been busy. They're really exciting, but they've got kind of a fundamental flaw, fundamental problem that we can't overcome by continuing to make more detectors on Earth. We can understand this a little bit better by looking at this nice colorful plot that's really hard to read. It shows the characteristic strain of different astrophysically relevant gravitational wave sources. So each of these colored things are different things that we could see in the gravitational wave spectra. The higher is the louder their gravitational signals are. On the horizontal axis is the frequency. So kind of more to the right is a faster gravitational wave signal, more to the left is a slower gravitational wave signal. And what you can see, this little black curve, is the sort of sensitivity bucket of the LIGO detectors. So our detectors on Earth can sort of see everything that's inside that black curve. But what you've probably noticed is that there's a whole bunch of really interesting things below that black curve at lower frequencies that are inaccessible to ground-based detectors because they're fundamentally limited by the seismic noise of our planet, the tectonic plates and the Earth moving around. Unfortunately, we cannot access these really interesting scientific measurements from Earth. And that's a pain because they are cool. Massive black hole binaries consisting of black holes of solar masses of 10 to the 4 up to 10 to the 8. So absolutely cosmic titans. Their mergers are these incredible tests of general relativity. We test things in the boundaries of where they work. And so being able to observe these mergers would let us really explore the kind of limits at which general relativity holds up or maybe breaks. Another interesting one are extreme mass ratio inspirals. These are when little dense objects, like small black holes, orbit around supermassive black holes, like Sagittarius A. It's the massive black hole at the center of our galaxy. As they orbit these massive objects, they do these kind of weird irregular patterns, essentially forming a gravitational wave function that maps out the geometric space-time of that supermassive black hole, something that would just be unparalleled science if we could interrogate these signals. But we can't. We can't from Earth because the seismic noise is too large. So we need to look for other options. The other thing it turns out is that to see things at these low frequencies, these slow gravitational waves, we need the arms of our detectors to be really, really big. These two requirements drove the design of the Laser Interferometer Space Antenna, or LISA mission. LISA is a mission that is kind of being spearheaded by the European Space Agency, but has significant input from NASA on scientific know-how, as well as NASA's delivering a couple of the key critical components of LISA. LISA is a space-based gravitational wave detector that consists of 3 satellites that are in an equilateral-ish triangle. The arm lengths or sides of this triangle are 2.5 million kilometers, so it is massive. LISA will follow Earth around the sun, sort of tumbling, and as it does so, probing the cosmos for these low-frequency gravitational wave signals. How does it do this? Well, those 2.5 million kilometer arms are kind of connected with lasers. We shoot lasers between the satellites in space to track the change in distance between them to the picometer level. When we do the maths for what this will result in, we see that LISA's sensitivity curve, that kind of black curve, is right in the bucket of the stuff we're interested in. It's going to do really awesome science, but it's not up there yet. LISA was first sort of kind of thought about in the 1980s in a different name, and then eventually it kind of permuted a little bit, and it's taken a while to really get it to a stage where we believe that we can make LISA. But fortunately, in January of last year, LISA reached the phase of mission adoption. What this means is that the Scientific Advisory Committee for LISA has said, yep, you've done all the tests and we believe you, let's make the thing and put it into space. This is really exciting. It means it's going up. The projected launch date is about 2035, but nobody ever knows with LISA, so it's going to take a while. Exactly why that's the case, let's have a look. See, LISA has a whole bunch of really complicated, hard to make parts. So maybe if we chat through some of the bits of it to understand how it actually operates, we'll see why it's going to take 10 years to build the thing and why it took 20 years, 40 years to even figure out if it would work. The heart of LISA are two of each of the 3 satellites are these 2 little golden cubes. We call them test masses. They're about 80% gold and 20% platinum. There's a photo of me holding a recreation of one. They're 2 kilos as well, so for their size, they're really heavy. And they sit sort of 2 of them at the heart of each of the spacecraft. Now, these cubes are like carefully wrapped in with some sort of containment enclosures, but they are completely free falling within the spacecraft, not touching any of the walls. They are the perfect references that we're going to make our measurements from and to. So we've got these 2 cubes, 2 golden cubes in the spacecraft. The next thing that sort of surrounds them is a complicated, massive optical laser system. And this laser system is sort of the workhorse of LISA. We have these pristine cubes that are kind of free falling in space, doing these laps around the sun. And the optical system is making a couple of key measurements. Firstly, it's measuring how the spacecraft is moving relative to that test mass, to the golden cube. And then secondly, it's sending lasers out across the 2.5 million kilometer length and measuring how the spacecraft is moving relative to the other far spacecraft. If we do kind of like a cube to spacecraft measurement, and then a spacecraft to spacecraft measurement, and then a spacecraft to cube measurement, we can figure out, using these optical links, how the displacement, the distance between these cubes is varying in time as they go on these massive orbits around the sun. Key to note, the laser, which is such a critical part of these missions for LISA, is actually being provided by NASA. They've just, I think, finished the first prototype and sent it off to Europe for testing, but they're working on kind of the next iterations of that. So we have this optical system and it's shooting this light. But the problem is that kind of all light as it propagates kind of naturally diverges and spreads out. If we just shot the light straight out of this laser across the 2.5 million kilometer gap between these satellites, by the time it reached the far satellite, the beam size of that small laser would be 100 kilometers across, which is basically impossible to make measurements with. The light is so spread out and dim, we couldn't possibly see it. So instead, what we need is a series of telescopes that help us sort of make that beam larger in a controllable way so that as it propagates, it diverges slower. These telescopes are actually being produced by NASA as well. They've just produced the first round of prototypes because we're sort of approaching the stage where we've got to make the real stuff. And those are at NASA Goddard. They're doing a whole bunch of testing. They are these pristine 30 centimeter ceramic plates. Yeah. So this is sort of like a couple of the bits inside LISA that show how it's so difficult to kind of build these optical systems and put them together. I'm going to pivot a little bit now and talk about ANU and some of the stuff going on here that's contributed to LISA and to other intersatellite laser missions for science. So I'm a researcher now as part of the Center for Gravitational Astrophysics here at ANU, where we do a lot of research that pertains to ground-based gravitational wave detectors, but also a lot of this sort of space-based laser research. So I'm going to focus on that a little bit more today. So one of the problems that we really focus on in our research is how well we can perform these sort of distance displacement measurements across these massive multi-million kilometer links. See, in the setting of LISA and these sort of missions, our laser is sort of like a ruler. It works really well like this. You can think of the sort of the wavelengths, the troughs and peaks of that wave as being like the ticks of a ruler. The problem, though, is that when the color of the laser changes and when the wavelength changes, that looks the same to us as our ruler stretching and squishing, which we interpret as a measurement and a change in displacement. So if the wavelength becomes longer, it looks like the distance between the spacecraft has become shorter. And same as it shrinks, it looks like that distance has become longer again. So for these missions to work, we need to be extremely particular in how we stabilize the wavelength of those lasers so that we can perform these incredible measurements. This is one of our sort of main research themes in the Space Technologies group at ANU. We look at kind of different techniques and ways of stabilizing the wavelength of lasers of our rulers so that we can make these precision measurements. How do we do this? Well, the fundamental idea is that we've got a ruler, and we want to measure something with it, but we don't know if it's changing or the thing is changing. So we put the ruler in something that's an extremely fixed length. We use ultra-stable optical cavities. It's sort of in that silver bin. You can see a picture of a cutout of one there. And the idea is we know that thing is a fixed length. So if we put the light through it and make a measurement of that thing, any sort of change we see in the length, we know must be the wavelength of the light. So we can sort of fix it and lock it down. All of our research in this has actually led to us becoming sort of a key contributor to JPL and a bunch of the sort of intersatellite laser tracking missions that they've got going on. We sort of regularly collaborate with them on that and figure out the best ways to sort of stabilize the lasers for these missions. We're also looking at some other interesting techniques like stabilizing them to really long lines of optical fiber, like the thing you would use for like internet and fiber optics at home. Turns out that you can use that to sort of stabilize a laser if it's kind of stable enough in length by the same principles. So this is one sort of area and region that we're kind of really interested in. Another one, which is near and dear to my heart, because it's what I spent 4 years of my life slaving away at, enjoy, is how well we can make and perform measurements with really small amounts of light. See, as we said before, these lasers are constantly spreading out as they propagate, which means that because they're multiple kilometers across by the time they get to the far satellite, and we only capture sort of a 30-centimeter disk of that received light, it's really hard to read our ruler. Weak light is the same as the ruler being extremely faint. It's really hard to see the ticks, so it's really hard to kind of judge how the distance and displacement is changing between the satellites. We've spent kind of multiple years working on this at ANU that sort of culminated in a tabletop experiment in which we could show that for different lasers, we could figure out how faint an optical signal you could still make robust measurements with it with. We actually went down to the order of single femtowatts of light, which is about 5,000 photons per second. Absolutely nothing for me as an optics person. That's oodles of light for a deep space network or oodles of photons for those sort of things. But the sort of techniques we developed and things that we showed were so interesting that some of our other colleagues at JPL who do this sort of stuff wanted us to bring our tabletop experiment over there and run some measurements with their lasers as well. Unfortunately, my experiment was messy and I had no idea what I was doing, but we managed to pack it up into a little box. You can see it on this right side that kind of fit nicely in carry-on. It was full of fiber optics, so I got stopped at every single airport because it was a suspicious box full of cables. But we got through, we got it to JPL, and in 2 weeks, we took a bunch of measurements with their lasers, actually demonstrating that if they used the parameters and the tunings that we had found in our lab, there was a 10-fold improvement that could be had in how low an optical power level these systems could operate at. This isn't particularly immediately relevant to LISA because LISA has a whole bunch of kind of fundamental limitations, but a lot of this research applies to kind of future space-based interferometric missions. They let us dream up different designs and configurations that we might not have been able to think of before because we didn't know how low an optical power level we could go down to. Anyway, I think this has been a nice, hopefully this has been a nice little overview into sort of gravitational astrophysics and the sort of role that space-based detectors can play in that. Mark 2035 on your calendar, because when LISA goes up, it's going to be exciting and the science is really, I think, going to blow us all away. Thank you.
Okay, so for the interest of time, we'll get one question from the audience and then we have one from the online audience. Okay, lucky hand up first all the way at the back there.
Thank you. This is a bit of a theoretical question, but say LISA is a successful project and we're able to get the wavelength data that you're looking for.
is there much benefit in sort of setting up, this is obviously very future, but setting up interferometers on other planets like on Earth? Or would it be sort of made redundant by having sort of more LISA projects instead of that?
No, that's a really good question. And it's the sort of thing that's being considered constantly in the gravitational wave community, what the sort of direction and next detectors are. One in particular that's being considered is the moon, because we know it's sort of lower seismic noise than Earth. So maybe there's potential for something there. The problem with these detectors is they're really hard to make, so they sort of need a superpower. LISA's superpower is that it is absolutely massive. It's like 2.5, 2.6 million kilometer arms. They're looking at ones to follow that are even bigger, like 250 million kilometers. As you increase the length of those arms, you actually increase your sensitivity to the gravitational wave signal. So that's the sort of superpower of these space ones. The superpower of these Earth-based ones is that we can have a full-time team of incredible nerds constantly tinkering on them and fixing them when they break and improving them and pushing down the quantum limits and doing all these incredible things to these sensors. One of the challenges with going to other planets and looking at these things is that if you go to a planet and you're not in space, you lose that length superpower. And if it's really hard to get people there, you lose your like super army of physicists and engineers to work on it. So that makes it a little bit harder. But particularly for the moon, it is being explored and considered.
Okay, lovely. So we have a question for Dr. Callum from Brisbane. Congratulations on your graduation. Throughout your undergraduate degree, did you participate in any summer/winter research programs? If so, how was your experience? How did it help you later in your degree?
Really good question. The onlines really love questions about our roots and where we came from. Hey, they're on that. What did I do? Summer and winter research programs. I did a lot of kind of special topics research programs here at the ANU, and I thought they were invaluable. A lot of the coursework I did was really good and really interesting and let me learn and taught me things. But it was the times when I got to just sort of go work with 2 or 3 people in the lab over the summer or even during the semester for coursework, when I got to actually tinker with things and get my hands on the bolts and break things and feel really bad about it. That's when I sort of learnt the most, but also learnt what I was interested in and what I was curious about. So yeah, I didn't, those were the sort of research projects I did and I really enjoyed them.
Lovely. So big round of applause for Callum here. And now we'd like to introduce Elisa from the Advanced Instrumentation Technology Centre. So come all the way down from Mount Stromlo Observatory and here to talk to you today at the Physics Auditorium. So it's a little bit further away, but we're still connected pretty well.
Thanks. Come through? Cool. I don't actually live at Mount Stromlo, though I actually live just down the road here, so it wasn't too bad. But yes, I've come a long way further than the NASA people. Irrelevant time, but I remember when I first looked up if my name had any scientific connections, and there is a proposed extended LISA, which is ELISA. So maybe we'll see that in the 2040s. I can't remember what it actually was. Yeah, so my talk's probably a little bit more ANU focused. I'll feed back a lot into what we have heard about before already. We've set up about communications in deep space, why we care, and how is Australia and ANU specifically contributing to those efforts. So I'm going to talk about space optical communications that we're doing here at ANU. That way? Well, was that you or me? Now it's me. Okay, cool. So what is that mouthful that was introduced? The Advanced Instrumentation and Technology Centre, or AITC. Basically, we're a part of the research school for astronomy and astrophysics, which is a pretty world-leading astronomy school that we have here at ANU. It's pretty exciting. But we don't do the astronomy so much. We build the instruments that go on the telescopes that allow you to do astronomy. So kind of vital, but we get a little bit less glory. So this is our facility up here. We're up on Mount Stromlo. We don't have so many active telescopes anymore after, unfortunately burnt down in the early 2000s. Good for me, that gave us a lot of insurance money to build some nice big labs so we can do a lot of instrumentation work. Yay, it's still sad. But we have some operating telescopes back on the mountain now. So this is basically the team, not the whole team because I wasn't even in that photo. We've got a bunch of cool facilities. So something you might have heard of is the Wombat XL. I hear there's a Wombat on campus, so specifically not that one. Basically, there's a thermal test chamber for spacecraft. So most small satellites coming out of Australia now usually go through their thermal testing at our facility. Basically, there's a lot of qualification they need to do to be like, know that they're going to survive in space. And we do things like shaking them and testing the vibrational, they'll survive launch, basically. So that's all the stuff that we do. Cool. Okay. So yes, cool. So recently, in the last few years, we've built the Quantum Optical Ground Station, or QOGS, up at Mount Stromlo. So it's the first, well, it's now the only active science telescope on the mountain. So we've got one back. Yay. This is a time lapse here of it being built. You can see the dome being lifted on from a while away. Unfortunately, it wasn't beautiful weather that day. So what we have is a 6.5 meter dome with a 70 centimeter telescope inside. It's a 2-story facility, so we've got climate controlled laboratory below. And that's enabling us to do a lot of research into advanced optical communications to space through all different orbits. We're also working on quantum communications, looking into space situational awareness. And then there's a lot of research in this field as well on site testing and atmospheric characterization, because in optical, the atmosphere is your main enemy. Nope, I went too far. Okay, so QOGS and the team, a bit more about us. Basically, this is some of the team here. We've got about 7 or so academics working out of the facility, professional staff, 2 PhD students. We've currently got 2 PhD scholarships that are open if anyone's interested. And we've got honors students, and we have undergraduate students coming through all the time as well. So the telescope we have is from an American company called PlaneWave. It's optimized for maximum throughput of your light, so you can get as much signal and then as much communication as you can possibly, well, not as much as you could want, but as much as you can get. So we're installing equipment on this telescope at the moment to enable optical communications in low Earth orbit, GEO, and then also through to lunar communications. And we're also building instrumentation systems like this one you can see tiny here that are doing adaptive optics. So that allows you to compensate for your turbulence in the atmosphere and gives you basically the improvements you need to do high performance systems. So our telescope here lives upstairs in the facility. Downstairs is our lab. And this pier here will to be installed, but will basically host a bunch of mirrors that will pass the light from the telescope down into the lab here. So we can set up large sensitive equipment on the benches and use the telescope to track our spacecraft and pass the light through. So I remember when I first started, I was very impressed. I was like, oh, it's called a coup d'eil path. Sounds very fancy. It's French. Basically, what that translates to is elbow. It's an elbow path, which is a lot less fancy when you say it in English instead of French. But it's just because you reflect the light at 90 degrees, so it looks like an elbow. But yeah, we still always say coup d'eil path. It's very fancy. Cool. Yeah. So as Kevin mentioned earlier, some of the things we're looking to be able to be compatible with and potentially support are optical communications to lunar spacecraft. So we are building the instrumentation system to go on our telescope that will be compatible with these systems. Basically, it uses this high photon efficiency standard. And what you're actually doing in this case is you've got your laser between the ground station and your spacecraft, and you're encoding your information just in tiny little pulses of lights. And the positioning of these pulses is how you encode the information. So it's different to coherent communications that you might use in RF a lot, where you're using the phase. But in this situation, when you're going to far distances, you basically need to scrape out everything you can out of your photon. So we go back to pulses. But it's still difficult to implement. So O2O hopefully be launching in 2026. We're trying to be have all our instrumentation built and ready this year. This is some design currently. This is what it will look like. I've got the instrumentation on the telescope. There'll be a receive system on the side here that will couple the received light into a fiber, and a transmit system at the top with 4 separate transmitters. So this will be what each of the transmitters look like inside. One of the difficulties you have with the atmosphere is it really distorts your beam in a whole bunch of ways. So if you have 4 different transmitters, you can basically average that out and get not as bad an effect, but it makes the system difficult to build. Cool. The main area that I work on is the receiver system. So I got to go over to Glenn Research Center last year and do a whole bunch of testing on all the equipment. The receiver system is difficult as the context has been established. We're not working with a lot of photons. So basically you're working with detector technology that detects each individual photon. And then you count those photons and you tell when they came, and that's how you get your information out. So the technology we're using is called a superconducting nanowire single photon detector, or SNSPD. There's a diagram here of how that works. Basically, you have these nanowires, which just means a really skinny wire, and you cool them down to about 2 Kelvin, and they become superconducting. And what happens is a little photon comes in, hits that wire, and that's enough to heat the wire up, so it's no longer superconducting for a short period of time. And basically that gives you a voltage pulse, and then you can count that you received a photon. So the system we have has about 16 of these wires. Well, it is 16 of these wires in a small array, and that's inside a cryo box. And then we basically use that to detect and count the singular photons coming in. That gets fed then to a FPGA-based modem, which does all the signal processing, because this is basically 16 different detectors all counting photons, and then they all kind of have their own timing characteristics. So it's fun most of the time. Sometimes it's annoying, but mostly it's fun. And then to do all this testing as well, I remember when I signed up to be like, yeah, I'll do the receiver side of it. That's fine. That's simple. That's just this. And then I realized to test the receiver, you need to build a whole functioning transmit unit to replicate your transmitted signals for the receiver to receive. So I also have to build a test transmitter. So just to do full end-to-end testing of that system, which is pretty fun. There's a lot of difficulty as well in making these optical pulses. We're kind of pushing the limit of what the technology is available. So, as you may have heard of Psyche. Psyche is a mission that NASA has put up, and they've done the furthest deep space optical links. You can see here a picture of Psyche. The optical terminal is quite small compared to the RF terminal, and it greatly outstrips the performance. I hope/wonder if many of you saw Taters, who reached internet fame for being transmitted. One of the main links from Psyche. It's definitely not made it a life goal for me to get my cat transmitted through space now. I mean, we haven't decided what we're going to send as our first signals, so it's a viable candidate. So Psyche's operating out to about 3 AU, so 3 times distance between the Earth and the Sun, which is about the kind of range you're thinking of when you're looking at communications to Mars. And as has been established, if your astronauts want to watch their footy, then they need optical communications. So, serving a great purpose. So how does this relate to us? The main ground station for Psyche is in the US, and ESA, the European Space Agency, is also setting up a demonstration to show their own capability. We happen to have a nice optical observatory here as well. Unfortunately, the telescope at Quogs is a little bit too small. You need something quite large to do deep space communications, just because you need a large collecting area to get enough photons to even detect those singular little photons. So the Sliding Spring Observatory is in New South Wales, about 500 kilometres north of here. It's actually completely run by ANU, so the Research School of Astronomy and Astrophysics runs that facility. This is the AAT, the Anglo-Australian Telescope. It's actually still quite active and quite a high-performing astronomy telescope in the world. It's got a 3.9 metre mirror, which is it's the biggest in Australia. It doesn't compare to some of the many 8-metre telescopes around the world, but it's still doing a good job. And it's still quite capable of well, it's very capable of potentially doing optical communications. So luckily for us, our work trying to be compatible with O2O means we're using these standards that are also implemented by Psyche, because it's a lot further, but it's still deep space. So the equipment that we have, these special detectors and this modem and the whole signaling process is the same for O2O as it is for Psyche. So we're working towards doing a capability demonstration where we're going to try and stick this equipment on the AAT and see if we can receive some photons, basically. And why that's useful is, as was established earlier with the deep space network, you want to maintain constant line of sight to your deep space assets. You want to be getting all the data down. So conveniently, the AAT fills this nice gap here between where the US site is and where the ESA site is in Greece. So some other stuff that we work on is looking at the Australasian Optical Ground Station Network. So basically, it's an informal gathering of research institutes, but we're looking at kind of building off each other and building a research network in Australia. So there's a uni over in Western Australia. We've got a group in South Australia and also some friends over in Auckland. Well, they're in Auckland, but their ground station is not. And why this is important is, as has been established, the atmosphere and the clouds are your biggest problem. So there's no real way to punch through the clouds, unfortunately. As cool as that would be, not feasible. You'd be just burning plasma into the air at that point, and you're not communicating anymore. You're destroying things. I'm not saying it's bad, it's just not what we're doing exactly. So pretty much the only way around that is to have a network of ground stations, and you can have planes, things in the sky as well, but you need options to connect to. And then there's a lot of work that goes into analyzing how do you design that network, where do they need to be, and then how do you build the different instruments at those locations, because those locations have very different atmospheric characteristics that aren't actually very well understood. So there's lots of ways to characterize the atmosphere, and there's lots of measurements on it at the top of mountains where all the astronomy telescopes are, because that's where people have normally cared. So people don't really know that much about the kind of turbulence characteristics you expect when you're at a shitty location in the middle of the desert. But the middle of the desert has really low cloud levels. And Australia doesn't have any mountains, not like huge mountains that are big enough to make a big difference for your turbulence levels. So you're going to have to deal with it. So one way we work around, one of the main technologies that we work on actually, which has huge implications for optical comms, but is also used very widely in astronomy, is adaptive optics. So basically what happens when you have light coming through the atmosphere is it gets this kind of, well, a lot of distortion, but it's basically why the stars twinkle, is it's coming through the atmosphere, it's getting distorted, and you just get this spot when you try and detect so this is just an image of a star, right? But that's a problem because you also get that spot when you're trying to detect your laser, which has communication signals, and you're trying to put that into a fiber, which is a small little thing, and it's like doing this. So that's not great. So basically what you do is you have these mirrors, which are deformable, and these little rods that push them really fast, like 2,000 times a second. What you do is you measure how distorted the wavefront is coming in, and then you correct that on your mirror, and that allows you to get a nice focus point, like here. Can I play it again? Yes, yes. So this is just a raw image of a star taken through turbulence, and then if you turn your adaptive optics system on, that's the resulting image that you get. So this is also used for things like space situational awareness. If you want to image a satellite, you want to actually be able to resolve its structure, not just see that there's a blob of something there. So that's some of the main research that we work on as well. And that's also a key enabler for the quantum communications. Because again, in quantum, you need ridiculously high performance. You can't lose any photons. You're working in singular photons. So you need to make sure you capture everything. So just briefly, how can you get involved? So if you're a university student, we do undergraduate research projects if you're interested in instrumentation or astronomy. Honours and masters. Also, we have 2 PhD scholarships currently open for application. So you can just go on the ANU scholarships portal and search optical communications, or you can just contact me. For general public, there are astronomy outreach nights at Mount Stromlo run very regularly. So feel free to come up. I'm pretty sure they're pretty easy to find online. And follow ANU InSpace. They post most of their updates. And then tours of COGS could potentially be organised if the Astronomy Society wants to or something. So yeah, feel free to hit me up. Thanks for listening.
You mentioned towards the end there that for, was it quantum? You need every photon, but as the number of satellites will increase over the coming decades from tens of thousands to hundreds of thousands, how do you foresee yourself getting around that? Or is that even an issue at all?
Do you mean like in terms of interference?
Yes.
Yeah. One of the good things with optical that you won't have with RF is, as Kevin mentioned as well, the pointing is very specific. So if I'm here and this satellite's talking to me, if it doesn't point directly at me, I'm not going to see it. And also, if I don't point directly at it, I'm not going to focus its light onto my detector. So it's actually an advantage depending on who you are. It's a huge security advantage for optical comms. It's really hard to eavesdrop. It's really hard to interfere with. So yeah, it's probably not likely to be a big problem, which is why we also don't really have spectrum regulation. And although most of the world doesn't regulate optical. So in RF, you need permission to transmit because you will interfere with people. Optical, you don't because it's so narrow. You're not going to unless you try, except in Australia where we regulate it. But don't ask them too many questions exactly about how. I shouldn't say that. Next question. Oh, sorry, muted.
Okay, so this will be our final question for tonight. I have short legs, so you'll just have to wait a moment for me to get the microphone up to you.
So I was wondering what the most challenging or most exciting part of your career has been, because it sounds like you've had a very long career. Or very exciting one.
Hey, thank you. I'll take the exciting version. I love doing the instrumentation part of it, but I would say working in the lab and instrumentation is the most challenging part because you see all these cool things that we do, but you don't see most of the time where it just doesn't work and you can't figure out why. And it's character building. And sometimes you're like, but why did I choose this? I could have just looked at the stars. But it's also really fun when it works, and I like to play with lasers and detectors and stuff. But yeah, that's probably the hardest part. Especially when you're on student timelines, like if your honors project breaks. It's definitely didn't happen.
Okay, lovely. So I'd like to give one last final applause for Eliza. And keep the applause going. So a big applause to all of our speakers here tonight. If I could have the 4 of you please come out the front, we have a little gift for you guys on behalf of the Australian National University.
Oh, are we? Yeah. Thank you. Thanks for coming. All right. So as we're come to the end of this amazing evening, I would like to thank again the ANU Research School of Physics and Tim for the funding and for this amazing venue, the CGA and OSCRAF as well. And also our amazing NASA and JPL guests and also at Mount Stromlo Observatory. And everyone online across the country, thank you for your amazing questions. And yeah, that's pretty much. But have a great night. Thank you for coming. Sorry, I forgot to thanks Rocketry. My bad. They got jacked off somewhere.
Happy birthday, Alan. Okay, lovely. So logistics for tonight. I know it's no surprise, but out through the way we came in, except there's card access on the doors. So we'll have representatives outside letting you out. So please don't panic if the door doesn't automatically open for you.
People with ANU, could you stand next to one of those things and just use your card, keep beeping people out? Thanks.
Okay, and the NASA JPL people, we have a few more things to talk about for afterwards, and then we can continue.
Rocketry and Astrosoc members, could you come down here for a second? Thanks.
And for the people who haven't left yet, my apologies. We also have some stickers from NASA and JPL for the NASA and Artemis mission. We'll bring them up as well, a few of them for by the door. Just a whirlwind of everything happening now. Thank you so much for coming tonight.
Hello. Sorry. Could I get everyone in the kind of in the center of the stage, and we'll take a group photo.
Can AstroSoc and Rocketry please get underneath the screen as well as presenters, ideally? Thank you. If you are not AstroSoc or Rocketry, can you please like step to the side near these banners just so we can get a photo? Thank you.